Hello everyone, welcome back to the AAS YouTube channel, and this is the good stuff. This is the AAS Journal Author Series, and I'm super happy to have Ilaria Caiazzo with us today. Hi Ilaria.
Hi Frank.
Where are you located these days? Where's your wave function?
I'm in Rome. I've been visiting. I'm actually at Caltech. I'm a postdoc there, but just in Rome for a couple of months.
Is that on a vacation, or is that COVID related or research related?
All of them, I guess. A little bit of visiting collaborators and family, and yeah, just working from a different home.
Cool, very good. Were you born in Rome?
No.
Okay.
I was born in Piedmont, the region of truffle and wine.
Very cool.
But I have family here.
Okay. So are you in an office somewhere there, or?
This is my Airbnb.
Airbnb, awesome. Very cool.
The living room.
Okay. How is, what's your impression of how the pandemic is going in Italy these days? I hear there's a second wave going through.
Yeah, well, I arrived here a few weeks ago, had to quarantine since I was coming from the US, which was a bigger hotspot at that time, but now it's going bad here as well. Cases are going up, and so they started like sort of a curfew at 6 p.m. Since today.
Okay.
So yeah, it's quite bad.
Okay.
Second wave everywhere in Europe.
Yeah. Well, of course, the US is a mess.
I guess the difference is here that almost a normal summer, while in California it was always kind of like this weird lockdown the entire time. Well, here it was normal summer, and now you're heading into some sort of lockdown again.
Headed into solstice. Well, let's hope things get better all the way around soon. So, Ilaria, what do you like to do for research?
So my main focus is on stellar remnant. I've done a lot of work on neutron stars. My thesis was on X-ray polarization in accreting neutron stars, black holes, and magnetars. But I work a lot on white dwarfs as well, and the paper is related to that part of my research. I'm very interested in magnetic fields, so how magnetic fields are generated in these objects and how they affect the physics and the observations. Yeah.
Very cool.
I'm a theorist, but since I've been at Caltech, I started doing a lot of observations as well, because there's so much glass over there. You want to take a bit of advantage.
The proverbial double threat where you can do observations and theory. So very cool. So this is going to lead us into this very lovely paper, which is a letter, actually, a APJ letter. Intermediate mass stars become magnetic white dwarfs. And Ilaria, take us away.
Yes, so this paper, let's put this in a little bit of a context. This comes from a bigger project that I have with my collaborators at UBC, and then Jeff Cummings and Jason Calirai and Pierre-Emmanuel Tremblay. They all, so this project is really to look at white dwarfs in clusters. And the reason why we want to look at white dwarfs in clusters is because we want to pinpoint their formation. So if you go immediately to a figure 4, I think, I can explain why looking in cluster for white dwarfs is useful.
Figure 4.
So star clusters are, again, clusters of stars that were all born approximately at the same time. That's figure 5.
Oh, sorry. Figure 4. My bad. Okay, here we go.
That's 3. Okay, perfect. So yeah, stars in cluster were all born about the same time. And so since stars of different mass evolves in different time scales. Heavier stars, bigger, more massive stars evolve first. And then, so you can see, for example, here in this figure, it was called a CMD, right? The color magnitude diagram. And these are 3 clusters plotted there. Blue, black, and red are 3 different clusters of slightly different ages. And depending on the age, you still see some of the more massive stars still on the main sequence. And as they go older and older, those massive stars are already gone. And so in this way, you can pinpoint the age of the cluster very well. Here you can see there's these 3 clusters, and there are 3 different ages. I don't exactly remember. I think, so the blue one is the younger one, and then the black one is the middle, and the red one is the oldest. And you can see that the upper part around the turn-off, some of the stars are already evolved in the red and the black cluster, while in the blue cluster, they're still on the main sequence. And so you can really pinpoint the age very well. And for this one in particular is one of the clusters we looked at. This black one is ACC 47. We were able to pinpoint the age of the cluster to be around 90 million years.
Okay.
So quite a young cluster. And so once you see that, you know which ones are the stars that evolved more recently. And so as you can see in the lower left part, there are white dwarfs in those clusters. The black one is the white dwarf of ACC 47. And so from comparing the age of the cluster and the cooling age of the white dwarf, you can figure out what was the progenitor of that white dwarf? What was the mass of the progenitor of that white dwarf?
Okay.
And that's why we were starting to look at white dwarfs in cluster, because we wanted to probe what's called the initial final mass relation. So what's the relation between the final mass of the white dwarf and the initial mass of the progenitor star, of like the main sequence mass of the progenitor star? Okay. And we were particularly interested in the high mass end of this initial final mass relation. So, because we know that, you know, it's for progenitor masses above about 8 solar masses, maybe 10, we don't know, stars go supernovae. And so we wanted really to look at white dwarfs around that mass to pinpoint what's the mass at which stars go supernovae versus creating a white dwarf. And so kind of like finding like the more massive white dwarfs and the more massive progenitors. Okay. And so that's what was the drive behind this search. And this paper is somehow a spin-off of that search, because we've looked at these 3 particular clusters that look very young, and we found these 3 white dwarfs that were somehow unexpected. But let me just say a couple of words on how we do this search and why this is somewhat easier right now than it was, you know, a few years ago. Okay. So maybe you can go to figure 1 now. Okay, so this is how we conduct the search. So before Gaia was there, the way people identified cluster member white dwarfs was just like by looking at, you know, pinpoint the white dwarfs in the same, you know, space as the cluster, and then figuring out that the white dwarf was probably at the right distance because of how the white dwarf looks like. While now we can use Gaia astrometry measurements, very precise astrometry measurements, to identify high confident cluster members. And we can do that with three different measurements, right? The parallax, which tells us the distance of the cluster, yeah, there on the left. You can see in gray, there's all the cluster members that we picked of the single star cluster. And in blue, there's the mean of the star clusters parallax, and in red there is the white dwarf parallax. As you can see that we can be pretty sure that the white dwarf is at the right distance of the cluster. And then of course you look at the rightmost panel is just in the sky, array and deck. Is it inside the cluster, close enough to the cluster? And then you look at proper motions, because all these clusters move together. If you look at how they move in the sky, they move in the same direction. And so you can also make sure that the white dwarf is not only at the right distance and place, but also moving with the cluster. So if all these three things check out, it means that you're pretty sure that this white dwarf was born inside that cluster.
Okay.
So Gaia has been amazing in this kind of searches, because we have so much information now that we could really pinpoint these stars as being cluster members. And so in our search, as I was saying, we focused on young clusters because we wanted to look for massive white dwarfs and massive progenitors.
Yes.
And so we found these three particular clusters with three white dwarfs. One of them, we already published about it before this paper. And that was kind of like the first one we found. And then we found these other two, and we were very surprised to see that they were all magnetic. So we found these three white dwarfs, and and there's not that many in that range. So maybe we can go to figure, don't remember which figure that is, figure 5, the first one you showed. So just to give a sense of why we were so surprised that these white dwarfs are magnetic. And then maybe I can talk on how we found that.
Maybe you'll get to it, but how do we know they're magnetic?
Okay, so let's then go to figure 2.
How do we
cover
how we know them?
So for these two parts, so for the first one we found, which is not shown here because it's in the other paper, it was pretty obvious that the white dwarf is magnetic. So what happens when white dwarfs are magnetic is that these absorption lines that we see in the spectra that are caused by electrons. In this particular case, this is hydrogen white dwarfs, so they have hydrogen atmospheres. And so you see these hydrogen lines are just caused, this in particular is the Balmer series, so electron jumping from the second level up, second to the third, etc., right? But when there is a magnetic field, these energy levels don't have just one energy, right? There's not energy level 2 and 3, but depending on the quantum, on the M number of the magnetic quantum number of the level, the magnetic field lifts that degeneracy. And so you have different energies depending on the M quantum numbers. And so what happens is that you don't have one line, the lines get split in 3.
Okay.
So delta M plus, minus, 1, or 0. And so you see triplets. If the magnetic field is high enough, you see triplets. And that's what we saw in the other white dwarf, which by the way was a helium white dwarf, like there's helium atmosphere, but it's the same concept. The lines get split in 3. And so for that one, it was very easy to identify a magnetic field of about 2.5 megagauss.
Okay, good. I'm with
you.
For
this one, for this one is a little bit harder because the magnetic field is a bit lower, around 1 megagauss. And so the triplet is blended. So instead of seeing the triplet, you just see one line that looks broader than it should be. And it's much easier if you just, for example, take now, here I'm just showing the different lines and the fits that I did on them. But if you just took the spectrum of M39, like this one on the left, and you compare it to a normal non-magnetized spectrum, the difference that you see is that at the bottom, the line looks more, I don't know if you can see me as well, but like the line looks not sharp at the end, but quite round. Here Exactly, you can see it a little bit with my rough magnetic models, but if you compare like this to a non-magnetized model, it's quite obvious.
Mm-hmm.
And then you can see it from H alpha, which is plotted separately in the bottom. Yeah, that one is just H alpha. You can see that both lines, both M39 and on the right, there's ACC 47. They all show some rough triplets over there, right? So often the central part of the triplet is much more pronounced, especially in H alpha. And then the other two are just hinted over there.
Yep.
Another reason why we were pretty sure that these guys were magnetic is that if you try to look at the lines without considering magnetic field, you find that the lines, if the lines were broadened only by gravity, then the white dwarfs would have a very, very big surface gravity, way too much for what you expect for a normal white dwarf. And so this white dwarf would have to be maybe 3 solar masses or something like that, something very not. So that was actually how I figured out there was something wrong. Like I tried to fit these lines for log G and I was finding it super high log G. So surface gravity, and I was like, wait a second, this doesn't make sense. And then I started looking at H alpha again, and then compared the spectra to non-magnetized spectra, and then it was clear that these guys were magnetic.
Okay.
So yeah, this one was a little bit more tricky, and a reason why I could really get a mass from the log G is that we have also a very good distance from these objects, again, thanks to Gaia. So it could be easy to mistake a magnetic white dwarf for like a more massive one if you didn't know the distance, right? So this is also a tale of caution for fitting lines. So yeah, that's it. So that's how we found they were magnetic, and then from as I was showing you before in figure 4. We get the distance, so we get the age of the cluster from fitting isochrones on the CMD, and then that way we also get the progenitor masses. And so if you look again now at figure 5, we can see how many white dwarfs we know in this range. There you go. So these are only white dwarfs in Gaia. So as I said, Gaia is very useful because if you see them in Gaia, we can verify that they are actual cluster members. For example, there are some other white dwarfs that were thought to be in clusters before that we checked for this paper, and they're actually not cluster members because, for example, there's the Pleiades, right? It's a very famous cluster, and there's all these white dwarfs that people say, oh, they're part of the Pleiades. Yeah, those two ones. So, for example, that one, the lower mass one, that's in the center of the Pleiades. That's the proper motion of the Pleiades. It's definitely a Pleiades member. The one that is the more massive white dwarf known, that is a cluster member, it's actually not a cluster member because it was originally associated with the Pleiades, but it is not. Huh. So there was a recent, yeah, I put them there in blue still because there was a recent paper using Gaia that associated, that's called GD50, that white dwarf, associated it not with the Pleiades, but with AB Doradus, which is a moving group. Okay. Which is somehow coeval to the Pleiades. Okay. So we could still put it there because you can still get somewhat of an age of the progenitor and therefore its mass from associating it to the AB Doradus group. Are one or both of these Pleiades white dwarfs, are they known to be magnetic as well? No, neither of them. And they've been checked also with spectropolarimetry, which is a very sensitive way of finding magnetic fields of even like a few hundred of kilogauss or even less. Mm-hmm. And at least GD50 was checked that way. The other one wasn't checked that way. But if you look at the spectra, there's no hint that they would be magnetic anyway. So no, those two, they shouldn't be. The question is like, do you want to consider GD50 or not as a cluster member? I decided to leave it there because we can still somehow get any progenitor mass from the Dorados group. So I just decided, also because people would have gotten upset not to see GD50 on that plot. Because it's the most massive cluster white dwarf known and people like it, so I left it there. But you can see there's no other above 5 solar masses except the 2 Pleiades ones.
Yep.
There was another one, again in the Pleiades, that was associated historically with the Pleiades because in one paper from, I think, 2006, someone said, this looks like it could be in the Pleiades, or like coming from the Pleiades, and that stayed in all the following papers. So we checked on that one as well, again using Gaia. And it's actually, if you go backward in time, you see that the white dwarf is actually moving away from the Pleiades. So it's at 20 degrees away, so it's far away. And it's also, you know, if you go back in time, looking at its proper motion is going in the wrong direction. So that's another one that, and we mentioned that in the appendix. I like that we did these checks. So the Pleiades has one white dwarf, and it's that one.
Yep.
So it says, you know, we found 3 out of 5, which with progenitor masses above 5 solar masses, and all the 3 new white dwarfs appear to be magnetic, which is, you know, a pretty high number. Of course, here we're talking about small numbers. You know, it's 5. It's not, you know, you have small number statistics, but it's still, you know, if you have to find, you know, if you have to pick out 3 magnetic white dwarf, picking out of 5 out of a distribution of 15%, which is what 15 to 20%, which is what is known in the field. It's still quite a big fraction, you know, 60%. So, and this is very interesting because maybe I can digress a little bit on why this is interesting and why for like how magnetic white dwarfs are generated.
Okay.
Because so there's a debate on why only 20% of white dwarfs are magnetic. Where do they come from? Where does the magnetic field come from? And there's different theories. It could come from, you know, the progenitor star. The progenitor star could be magnetic. And we know of magnetic A and B stars, which could, you know, the magnetic field that we see could account for the one that we see on white dwarfs, but they're not enough. You know, they're not enough to explain 20% of white dwarfs.
By number, okay.
Or it could be that the progenitors have some magnetic fields, but it's hidden. And there's been a lot of studies recently on astroseismology that show that there could be hidden magnetic fields inside the core, inside the convective cores of main sequence stars.
Yep.
And red giants. And so this is a possibility, right? Like, so it comes from the progenitor star somehow. And the other possibility is that it comes from binary interactions. A good hint to that is that we see that about 25%, I think, of CVs are magnetic. So accreting white dwarfs are magnetic.
Okay.
But there's only very, very few white dwarfs known that are magnetic in a binary with the main sequence stars. And I'm talking 2 or 3.
Okay.
Very, very, very few. And so that's why a lot of people say that you need some binary interaction to create the magnetic field on the white dwarf. So you might have dynamo and convective envelopes or during the merger. So and it's a lot of people are actually believe that white dwarfs, magnetic white dwarfs that are isolated, are actually the result of mergers, right? And then the reason why we don't see that many in a binary with another white dwarf or in a main sequence star is because you didn't have any form of binary interaction when you're on the main sequence.
Okay.
And these white dwarfs that we find, I think they kind of disprove the theory that you need a merger for a white dwarf to be magnetic, because these clusters are very young. One of them is 90 million years old, so it cannot have created two white dwarfs that are low in mass enough to merge and not go supernova and create a one solar mass white dwarf, right? So the double white dwarf merger scenario, it's very hard. You can imagine, I don't know, on the main sequence, you have some, as the binary evolves, you have some mass transfer, some mass is lost, and one of the final white dwarf is very low mass. But it's very hard to have three white dwarfs, which are also the first white dwarf born in those clusters, to have gone through such a weird evolutionary scenario.
Right. Okay.
So I think it's fair to see that these white dwarfs have not merged. They're not like double white dwarfs mergers. They could come from mergers on the main sequence, and that's why they're peculiar. But then you're like, again, moving something to the progenitors. Maybe the progenitors are mergers somehow, but that's opening another different topic. I think this white dwarfs tells you also because their age agrees with the age of the cluster. Like you don't need any delay or any other, or less time. They seem to come from single star evolution. So I think this one tells you that magnetic white dwarfs can be born from single white dwarfs, so single stars. And the finding that many in this range may also tell you that more massive stars are more likely to become magnetic white dwarfs. And hence the title, intermediate mass stars become magnetic white dwarfs.
Plus mergers are messy, right? I mean, it gets thrown off. You would think that you would see some shell of material, perhaps,
Yeah, one of the white dwarfs is also very, very young. Like the one in ACC 47 is only around 100,000 years old.
Mm-hmm. Okay.
So very, very young. Yeah, and it doesn't show anything weird except it's very, very hot.
The simplest explanation is a great starting point.
Yeah, exactly. I still think that mergers definitely create magnetic white dwarfs. If you find, especially the extremely high field ones, hundreds and hundreds of megagauss,
Yep.
Those are likely to be merger remnants, especially if they're rapidly rotating.
Okay.
You have a lot of hints that those are merger remnants. So I think there's actually different ways to make a white dwarf, but somehow I think you can make them also from single star evolution.
Mm-hmm. Certainly. Okay, cool.
Yeah, this is all there is in this paper. Of course, I don't think it makes sense to go into the appendices because it's all about like how I fitted the spectra and the lines and my Monte Carlo simulations and all of those things. But I think most of what's in the paper is here. And then, so as I said, this is part of a bigger search that is led by Harvey Richer and Jeremy Heil at UBC. And what we're doing now is, we found, it is a bit of a spoiler, we found very few white dwarfs in this search inside the clusters, way less than that. And so what's next is I think what's really happening is that these white dwarfs get kicked, get kicked out of the cluster. They get doing, when you form a white dwarf, they can get maybe 1 kilometers per second or some very, not extreme velocities, but that's way more than enough, that in a few million years, the white dwarf is gone. These clusters are very small. And so the next step is going to be hunting for those escaped white dwarfs and try to figure out where they are and how they look like, because we didn't find, as I showed you, like those are the more massive ones we found, and they're all about like 1 solar mass, 1.1 solar mass.
Yeah.
Except for GD50, which is this,
Massive one.
Strange one. We don't have very massive white dwarfs at all, that we are sure they're single progenitor white dwarfs. And the only way to be sure is really like if they're in clusters. So maybe they don't exist. Maybe you need mergers to go to that high mass, or I think the answer is just they were the first to form and had time to escape. And so we have to hunt for them around the clusters.
Cool. So there's lots of exciting stuff to come over the next 5-10 years. I'm looking for magnetic white dwarfs. Very nice.
Yes. There's so many things you can do. Like I think there's not understood yet with white dwarfs. Like the models that we have, they're not the greatest. Like they're pretty good for regarding absorption features. But as you go to like very high magnetic fields, they don't work very well. And in my other projects, I'm finding a lot of very magnetic white dwarfs. And so I think there's going to be a lot to learn about magnetic white dwarfs in the near future.
Do you know if there's any magnetic white dwarfs that are known to pulsate, either as DAVs or DBVs or something like that? Are there pulsing magnetic white dwarfs?
That's a good question. I don't think so.
Yeah, because it seemed like if you did find one, that would give you a nice lever point on what's going on in the interior of those.
That is a very good question. I don't think they're known. So there's a lot of like variable magnetic white dwarfs, and but they're usually thought to be rotating.
Oh, okay. Okay, I'm gonna do a little search.
Because white dwarfs are usually not variable unless they're pulsating or they're magnetic. And I don't want to say something stupid, but I don't think there's any magnetic white dwarf known to pulsate. That would be very interesting.
Yeah, I'm gonna do.
One of the projects I'm working on is with a Zwicky transient facility to look for rapidly variable white dwarfs, and I found a lot of them. Like this is again a bit in the future, but I found a lot of them, and most of them appear to be magnetic.
Great.
So maybe one of them is going to be pulsating instead of rotating, but it's going to be, it's only the period that can tell you that, right? The period and the composition, I guess, like the atmosphere composition. I think if the period is fine to be rotating, I think people usually assume that they are rotating. I guess you can figure that out. From the light curve, maybe.
Right.
But
cool. Lots of interesting avenues to explore here over the next decade or so in this field. It's very cool. Ilaria, thank you so much for taking some time and walking us through your really lovely article.
Thank you, Frank, for having me over.
Okay, everyone. Thank you so much, and we'll see you on the next one. Bye-bye.